Hello? Are there any questions as to the energy density and the derivation of that? Is that you understand what the term means? No questions? Thank you. So now we will leave this new result for later use for a while and get to the third important field that is present in a static universe. So we had electric field where charges that do not move affect each other by force. Then we have steady current which flows as a result of electric force and which is a transport of charge. So we have moving charges due to the electric field that forces it. And then we have a magnetic field, which is a way how moving charges exaggerate force on other moving charges, or we can tell currents affect other currents by force. Now, this is all about charges, steady or moving. And moving charges, or as a synonym we can say currents, affect other moving charges by force, and this force we call magnetic field. Now we will start from the very beginning again and define the first terms. So we, quite like in electric field, will have two important values. The first is H, a kind of equivalent of the field strength in electrostatic field, which is measured in ampere per meter. And we have the flux density, B, which is measured in Weber per meter. We have again those two values connected by a material equation so that B is in a linear homogeneous isotropic media directly proportional to H by a coefficient that is called permeability. Now, permeability is again dependent on material as a material constant. It is worth to remember its value for free space. The permeability free space mu0 is exactly equivalent to 4 pi multiplied by 10 raised to minus 7 order, and it's measured in farad per meter. Likewise, in electrostatic field, if we integrate flux density over a certain surface, we get flux. So we have electric flux, we mostly denote it by phi, and this is an integral over some surface S of B scalar product with ds. I would put here a vector. So this is the magnetic flux, and as you can see, it's measured in Webers. Now, with those values, we now ask for an important law of nature that would give us the possibility to connect this magnetic field with electric current. As at the beginning I told, the current is the source of electric or the source of magnetic field. It causes the magnetic field. Then we would need some equation, and the first and most simplest equation that provides this connection is called Ampere's law, and it states that an integral over a closed loop of H scalar product with dl is equivalent to the current. Now let's comment it a little bit. The dl is the differential element of the loop. So for example, if I join my hands, we have a loop from my body, and the differential is an oriented vector on the loop. Now, having that, we know that we will have some problems in calculating this value. First, we have here a scalar product, and the situation is quite simple to the situation where we have been trying to establish the integral in the Gauss law at the beginning, when we had the integral over a closed surface. So now we would need possibly, to be able to evaluate this, we would need somehow from geometry given the condition that h is constant on some part of that loop, and we would need to at least know the angle between h and the element of the loop. Without that, the law would be valid, but will not be very useful for our calculations. So let's try to investigate the case in which we can use this law to find out some magnetic field.
Excuse me, sir.
Yes?
Could you please read the formulas you've written again? It's just the connection is not very good, and it's kind of hard to see.
Okay, so I have written two equations now. The phi, which is the magnetic flux, the total magnetic flux flowing through a surface S, is given by an integral over the surface S, and the integrand is B, flux density, dot product with ds, which is the element of the surface. So that's the first equation, which defines the total flux out of flux density. And the second equation, which is called Ampere's law, says that if we integrate h dl, so a dot product of the intensity and element of the line of the loop over a closed loop, we obtain the same value as is the current that flows through the loop. So just if we have the loop, for example, we put a membrane on that like a drum, and we integrate the current density flowing through the drum's membrane, we would get the total current. So the current flowing through the loop is this current. And we know that the current causes magnetic field, and if the loop has a symmetric and nice shape, we can carry out the integral, which we would do on the next page.
Thank you.
Thank you for the question. So now let us consider the first case. We have a long wire, long straight wire, which ranges from the minus infinity to the plus infinity and carries a current of I. So we have the current of I. I would draw it in the cross section. So we have the wire that carries the current from minus infinity to plus infinity. Then, if we have the integration loop, the integration path, which is a circle that has its center in the center of the wire, we have a special situation. First, due to symmetry, the value of magnetic field on the surface or on that loop must be constant, the magnitude, and the direction of the field must have a fixed angle with the element of the loop. And in fact, both are collinear, so both the L and the magnetic flux density and the intensity have the same direction. And now, this is a case that we can integrate easily. If we have two collinear vectors, the magnitude of their product is the product of the magnitudes. That's simple. So we can now write that we have BdL multiplied by the length of the loop, which is 2πr. So if the loop has the radius of small r, the length of the loop is, by Pythagoras, 2πr, by Archimedes. Then we have 2 pi r h equivalent to I, where I is the current, h is the strength, the intensity of the field. And now we can establish h is now equivalent to I over 2 pi r. Is that readable with your connection? Hope so.
Yeah, barely. I mean, sometimes it just goes.
Well, I hope that the other camera, which is a high resolution one, would put there on YouTube with a better resolution, unless YouTube damages it. Okay, so anyway, we have now the equation which says that we can calculate the field at this loop by dividing the current flowing through the loop by 2πr, where r is the radius of the loop. So, if we have a straight conductor of a negligible cross-section which is alone in a non-magnetic media, we would get the field strength inversely proportional to the distance from the wire. Now, we could also obtain the flux density B, which is equivalent to I over 2 pi r, and we multiply that by mu, which is the permeability of the media surrounding the wire. So for this case, we can establish both values They will possibly ask, well, and what about the potential? We have always established a potential in the electrostatic field. Well, I have a tricky reply. Well, in this kind of field, in magnetic field, we cannot introduce a global potential because a magnetic field is given by circulation, and that's a kind of field that has no potential. So in this field, we cannot introduce a potential that would be valid for the whole space. So let's forget about potential. We have only flux, we have only strength and density. So this is how we can solve the field around a current that is flowing through a small cross section of a wire. Now, on the last page, I have mentioned that we have a property of a material that is called permeability, mu, and that we have materials with different permeability. Now that ranges quite a lot, and we have roughly classified materials into, let's say, three important groups. The first group is called paramagnetic. Paramagnetic materials behave or interact with the magnetic field in the same way as free space. They do not affect it at all. This property we call paramagnetic. Then there are materials that affect the field a lot. Mostly those are metals, which are called ferromagnetics. Some of those are metal oxides, which are called ferrites, and this we call ferrimagnetic. Those two groups are important in that their relative permeability is bigger than one, or the permeability is bigger than the permeability of free space. If you get a magnet, those objects tend to be attracted to the magnet, and therefore they can move, and there are quite important forces. And we have the third group, which is called diamagnetic. Diamagnetic, and those are materials that have their relative permeability less than 1, or their permeability is smaller than the permeability of free space. Now, there are a few materials that you can meet in daily life that behave in a diamagnetic way. It's water, it's copper, but there are very, very little diamagnetics, so that you can't experience it without very precise measurement apparatus. The point is that they are repelled out of the magnetic field. There are materials that are very strongly diamagnetic, but you can't meet them in everyday life. Superconductors are diamagnetic, so that the magnetic field does not enter into a superconductor, mostly, which means that if you have a piece of superconductor, it is strongly repelled out of the field. That is, if you have a permanent magnet and you have a superconductor and you put it over it, it just flows on the magnetic field and is repelled so that it is levitating. In fact, even there are made some bearings that have low friction using superconductors that levitate over the magnetic field created mostly by not permanent magnets but by some windings, some coils. But anyway, those are the kinds of materials. So we have paramagnetic, which do not interact with the field more or less, ferromagnetic or ferrimagnetic. Both of them have permeability bigger than permeability of free space, and therefore they are attracted into the magnetic field. And there are diamagnets that are repelled out of the magnetic fields. Now, while diamagnetic materials at the time being are not that important, ferro and ferrimagnetic materials are produced in order to handle magnetic fields, in order to shield objects from magnetic fields, in order to change the shape of a magnetic field, and more or less ferromagnetic material and ferrimagnetic materials can act somehow like conductors in current field. Therefore we create magnetic circuits like electric circuits out of those materials to guide magnetic field. Such as an example of such circuits, there are transformers, for example, where you create magnetic field and use it and you guide it so that it somehow does not leak out of the circuit. I thought somehow because unlike in the case of electric current, where we can achieve a big ratio of many orders of magnitude between an isolator, insulator, and conductor, which the ratio could be like 10 raised to 15th order. In the magnetic fields, this ratio typically is 1000. There are some special materials like permalloys and supermalloys which could reach even 1 million, but only in special conditions. And this is not very useful to create real consumer circuits and distribution circuits. So the ratio in real magnetic circuits mostly is about 1000, which means that there is some leakage. So if you have a transformer in the circuit that feeds your notebook, then you have some leakage around. With a precise instrument, you can hear that, you can detect that, and it somehow also affects your body, for example. So this is the main classifications of materials with respect to magnetic field. We have noted that there are para, ferro, ferri, and diamagnetics, and we have noted that especially ferromagnetics and ferrimagnetics are heavily used in the industry to create magnetic circuits. Now we have not been investigating the inside of that materials. We have not raised the question why some materials are ferromagnetic while others do not interact with the field, but that's not a topic of this subject. Your questions, please.
I have a question regarding the formula for
Yes,
magnetic field and flux density. So the difference is only in the permeability.
yes, because this
And
is directly proportional to this with the constant of permeability. So if you have just to multiply it by permeability, so that those formulas are more or less the same.
okay.
Now we have established a simple formula for the field around a magnetic source, which is one stick or one thin conductor with current. And now we'll switch to another topic, which is boundary conditions. We have started electrostatic field, and we said, okay, there are materials of different properties, of different permittivities in that case, and we have to discuss what happens at a boundary between two materials with different permittivity. Then we have been talking about steady current field. We have noted that there is a property called specific conductivity, and we have discussed what happens on a boundary between two materials with different specific conductivities. Now we reach the point when we have magnetic field. The important property here is permeability, and again we can get a boundary between two regions with different permeabilities. So what would the conditions be? So first, let's have again a boundary, and doing that much like the previous cases, we have anything which is over the boundary marked by 1, and anything which is under the boundary is marked by 2. But if this is purely seen today, I will use Latin numbers, which could be distinguished better possibly. So let's say 1 and 2. And now, let's first formulate the situation for tangential components. We will again break any vector quantity to its tangential and normal part. So what about tangential components? Here we can use the integral law we have already used, that's the Ampere's law. Just imagine we have a closed loop that goes over the surface, then traverses through the surface just closely under the surface, goes back and traverses back. So we have a closed loop that is very thin in this dimension and just encapsulates the surface where we have the difference between one and other permittivity, permeability. Now, the law says that the integral over this loop, that is exactly the integral of h dot product with dl over this closed loop must be the current flowing just there through the loop. Now, yes, we might have current there if the surface is conductive. There might be some current. So we have to consider that. So first, let's get to the case when there is no current. For example, we have a ferrimagnetic device. Ferrites are not conductive. Their specific resistivity is very high. So they do not conduct electric current, but they conduct magnetic field. So this is an important point. So if there is no current there, then the integration loops as to tangential components gets some amount here and now goes in the opposite direction here, and the only way to get zero result here is that the tangential components upstairs and downstairs are of the same size and they are in opposite directions as the loop element. So for no current we would have a very simple condition which says that tangential component over and under the surface match each other. So once there is no current, those tangential components must be identical. But if we allow some current to flow through the loop, then the difference between those two values must be the current flowing here. So for example, if we say we would measure it over 1 meter, that would be the total current. If we want to get the same formulation, we would have to carry out or to work with current density. Now the density of current in this case means a current divided by the width of this surface. So it will be ampere per meter, the same unit as is obtained for this magnetic field intensity. So we can finally write down that in the case of a current flowing on the surface, we get the difference as the electric current's sheet density, and this is K. So the dimension of this equation is ampere divided by meter, and the K is the current density flowing on the interface between two magnetic materials. So we have a complete boundary condition in the case of presence of some sheet current flowing on the surface of one of those two magnetics. Now we should again return to magnetic flux density, which is B, and we obtain that by multiplying by permeability. So we can state, at least for the case where there is no current, we get the implication that B tangential 1 divided by B tangential 2 is mu 1 divided by mu 2, so that the tangential components at the interface between two magnetics, two non-conductive magnetics, are proportional to permeabilities of those two materials. Is there a question, please? So if there is no question, we can go on. There are two important laws that bend magnetic field. The first is the Ampere's law. The other law is even a bit more simple. And this law says that if we have an integral over a closed volume, of magnetic flux density multiplied or dot product with the surface element, we get 0. Just remember, this is quite similar to the Ampere's law in electrostatics, where we had d, electric flux density, ds, and on the right side there was q, the charge inside that closed volume. In this case, we state there exists no magnetic monopole. Magnetic field is a circulation. It has no origin or start and end. It is a closed loop at any time. And this law tells that. Now, having this law, if we put any volume that is partially inside, partially under the interface, and partially over the interface, we would find out that this integral law directly means that normal components of magnetic flux density B must be identical upstairs and downstairs. So B normal 1 is strictly equivalent to B normal 2. And therefore, we can also write an equation for strengths, for intensities, and now H normal 1 divided by H normal 2 is mu 2 over mu 1. So the normal components here are inversely proportional to the permeabilities of those two materials.